What up, Algebros? This is Arna from your Calc 3 class. Today we're going to be covering section 11.4, which goes over some applications of partial derivatives, which we learned about last week. Specifically, we'll be discussing tangent planes and linear approximation, as well as differentials. So before we get started with the questions for this video, just wanted to recap some of the important formulas. So when we're doing linear approximation, for example, if we have a surface such as z equals f of x comma y, we can say, we can write that as the tangent plane at the point a comma b, and then use that to help us approximate any given point. Also, we learned about differentials, which we can use to help us approximate change in z or the change in output, depending on what kind of function you have, because sometimes it can be a function of more variables than just x, y, and z. Cool, so let's get started on the first question. So we're given a surface z equals the square root of x squared plus y squared plus x times e to the y. And we're asked to approximate f of 2.95 comma 0.1, and notice we can use the point 3 comma 0 because it's pretty close to what we're asked to approximate. So remember, what we're first going to do is really we're just looking for the tangent plane, and then we can plug in our values to get a linear approximation. So if we look at the formula, note that we have to find the partial derivative with respect to x, partial derivative with respect to y, and then just f of a comma b. So in this case, f of 3 comma 0. So let's start with that. So f of 3 comma 0. Let's go ahead and plug that in. We're going to get the square root of 9 plus 3 times e to the y. So 3 times e to the 0. And that's going to be 3 plus 3, right? Because we know e to the 0 is 1. So 3 plus 3 is just 6. Awesome. Now let's find the partial derivative with respect to x. So fx is going to be, notice that we're going to have to use chain rule for this first part right here. So x squared plus y squared, since it's in the square root. So we can treat y squared as a constant. So when we take the derivative of the inner term, the inside, it's just going to leave us with a 2x. And then remember, because it's in a square root, we have to bring down a 1/2. And then we're going to rewrite the inside term, which is x squared plus y squared. And we're going to lower the exponent by 1. So that'll give us negative 1/2. And then for plus x e to the y, again, e to the y can be treated as a constant. So just the derivative of x, which is 1. So we get plus e to the y. Cool. And then just simplifying that, we know 1/2 times 2x is just x. I'm going to write this part in the denominator, x squared plus y squared. So we have the square root of x squared plus y squared, and then plus e to the y. Awesome. And then same thing for partial derivative with respect to y. So same thing with the inner term, except now we're treating x as a constant. So we're going to bring down the 1/2 from the square root. Then the derivative of y squared is just 2y. And then again, the inner term is going to be x squared plus y squared. Whoops. Let me undo that. Give me 1 second. X squared plus y squared to the negative 1/2. And then we have plus x times e to the y. So this time we're going to treat x as a constant, and since it's being multiplied to e to the y, we'll just leave it there, and we know derivative of e to the y is e to the y. So this is just going to be x times e to the y. And then again, let's simplify this. We're going to get y over square root of x squared plus y squared plus x e to the y. Awesome. Now let's go ahead and actually find what each of these are at the point 3 comma 0. So looking at the first one with respect to x, 3 comma 0, let's go ahead and plug it in. That's going to be 3 over the square root of 9, which is 3. So we get 3 over 3 plus e to the y, which is e to the 0, right? So we're going to get 1 plus 1, basically, which is just 2. And then same thing, partial derivative with respect to y at 3 comma 0. Let's go ahead and plug it in. So we know y is going to be 0, and it's in the numerator if we're looking at this part right here. And we know the denominator is not going to be 0, so we can go ahead and say the first part is just 0. And then let's figure out x times e to the y. That's going to be 3 times e to the 0, which gives us 3. Cool. So now we know this, we know this, and we know this, which is enough information to help us write down the equation of the tangent plane. And then we can go ahead and approximate this point right here. So let's go ahead and do that. So I know that we're going to get an equation which looks like this. So we said f of 3 comma 0 plus f at x 3 comma 0 times x minus 3 plus fy 3 comma 0 times y, right? Because y minus 0 is just y. And then let's go ahead and plug in the values. So we said that f of 3 comma 0 is 6, and f of x is 2, f of y is 3, right? So we're going to get 6 plus 2 times x minus 3 plus 3y, right? Yep, that's a 3. Awesome. 3y. Cool. And then let's go ahead and actually approximate that point. So 2.95 and 0.1 is what we said, right? So let's go ahead and plug this in. We're going to get 6 plus 2 times, and then 2.95 minus 3 is negative 0.05 plus, and then we have 3 times 0.1. Cool. So this is going to be 6 minus 0.1 plus 0.3, or 6 plus 0.2, which is just going to leave us with 6.2. Now let's actually check how good our approximation was. So what we can do is we can go ahead and actually plug it in, which is what I did beforehand with a calculator. So if we actually evaluate f of 2.95 comma 0.1, we're going to see that we got 6.2119. So that's pretty good approximation. And yeah, you can answer pretty much all questions like this. Just follow the same pattern. Make sure you know the formula. Cool. Now let's take a look at the second question, which is going to be asking us about differentials. So this one, if you want to find this question, I got it from the WebAssign on 11.4, and it's the very last question. So this one's split into two parts. So first, it's just practice finding the differential. And then we can go ahead and what it's asking us to do is compare the change in z with the approximation, which is what we're going to find. So let's evaluate this. So we see that z equals x squared plus 6xy minus y squared. So I know partial derivative with respect to x is going to be, let's take a look. So x squared becomes 2x plus 6xy. So y and 6 are the constant. So this is just going to be plus 6y, right? Because derivative of x becomes 1. And then minus y squared will just drop off. And then, so we have this times dx. And then same thing, but partial derivative with respect to y. So x squared drops off. 6xy is going to become 6y, or sorry, 6x. And then minus y squared is going to become minus 2y, and then times everything times dy. Awesome. So that was really easy to find. So now let's go ahead and actually compare the change in z with our approximation. So it's going to ask us if x changes from 2 to 2.08 and y changes from 3 to 2.95, See if we can compare the actual change in z with the approximation. And the way we're going to get the approximation is using this equation, which we just found in part A. Cool. So if we go ahead and actually plug it in, if you want to find the exact change, the way we would do that is we'd actually plug in f of 2.08, comma 2.95 minus f of 2, comma 3. And when we plug that in, we are going to get about 1.4399. And this is what you get if you plug it into a calculator. So let's actually check if our approximation gives us something close. So let's use the formula right here, this one right here, which we calculated in part A, and go ahead and plug in these values. So we know dz equals, let me go ahead and check. So 2x plus 6y, 2x plus 6y dx, and then plus, and then we said 6x minus 2y times dy. Cool. So first let's find on the side here real quick, let's find dx. The way we do that is we do 2.08 minus 2, which is 0.08. And then same thing with dy, we're going to do 2.95 minus 3, which is negative 0.0, oh, running out of space there. Negative, let me maybe write it down. We're going to say negative 0.05. Cool. So let's go ahead and plug in all these values. So we're going to plug in 2 for x and 3 for y, and then we know what dx and dy are. So we're going to get 2 times 2 plus 6 times 3, which is 4 plus 18, so 22 times dy, which we said was 0.08, or sorry, dx, which is 0.08. And then same thing, 6x minus 2y, that's going to be 6 times 2, minus 2 times 3, which is 12 minus 6. So we're going to get plus 6 times dy, which we said is negative 0.05. And then if we evaluate this, we are going to get an approximation of 1.46. So dz equals 1.46, but we're saying this value is our approximation of the change in z, or the change in the output of the function. And if we compare these, right? So we said that dz is 1.46, and we said the actual change in z is 1.44 basically, if you round. And these are pretty close. So next time you're in a life or death situation without a calculator, and you need to approximate something, you'll be good to go. The world can count on you. All right. That's it for 11.4, so thank you for watching.